Imagine an organization attempting to ingest its entire institutional memory into an AI. The standard enterprise playbook looks something like this. A team spends 6 months preparing proprietary data, spinning up expensive hardware, and running fine-tuning jobs on a base model. At first, the metrics look promising. The model adopts the company's specific terminology, it matches the corporate tone, and strictly follows internal brand formatting. But then it reaches production. Users ask domain-specific factual queries, and the hallucination rate is roughly exactly what it was before the 6 months of engineering effort. The model successfully learned to speak the language of the organization fluently. It still gets the actual facts wrong. Investing heavily in this process feels intuitive to teams accustomed to traditional software. Architecturally, however, it is an entirely mistaken approach. Mechanistically, why does a language model easily learn how to speak like an organization, but fail to learn what that organization actually knows? The answer lies in a core architectural constraint. Fine-tuning alters a model's behavior. It does not reliably install new knowledge. To understand why, we contrast data storage with neural networks. In the database on the left, inserting a single fact is a clean surgical operation. You add a record to an empty row, and the rest remains perfectly intact. In a neural network, factual knowledge is not stored in a discrete location. It is deeply entangled across millions of distributed statistical weights. When you attempt to force a new specific fact into this web through training, the update inherently disrupts and corrupts those adjacent representations. Fine-tuning is a behavioral routing mechanism. Treating it as a knowledge injection system directly fights the mathematical structure of the model. To see this physical constraint in action, we need to look at the underlying architecture of a base model. During pre-training, massive clusters of hardware compress vast patterns of human language into billions of floating-point numbers, or weights. This produces a highly capable general-purpose pattern matcher. Fine-tuning takes those exact same weights and applies gradient descent. It nudges them slightly toward the patterns found in a much smaller, specific dataset. Crucially, this process does not add a dedicated knowledge module. It does not create a separate, isolated domain-specific layer. Every gradient update modifies the very same weights that already encode everything the model absorbed during pre-training. Every adjustment made to force the model to mimic the fine-tuning data inherently makes it slightly less like everything that came before. This explains why behavioral updates succeed, while factual updates cause structural disruption. Traits like output format, the specific brand tone, and instruction following are surface-level patterns. This diagram illustrates the distinction. The model doesn't need to reorganize deep internal representations to learn that a response starts with a corporate summary. Factual updates are different. Changing one specific fact requires modifying deep patterns tightly entangled with entirely separate concepts. This update propagates through the multidimensional weight space in ways that cannot be mathematically predicted by the training signal alone. You can, theoretically, force a model to memorize a new fact through brute force repetition in the training data. The cost is extreme inefficiency and heavy collateral damage to the surrounding network. The empirical finding that fine-tuning improves behavioral consistency but fails factual reliability is an inescapable physical constraint of how the network encodes information. Recent empirical literature confirms this mechanistic breakdown, particularly a 2024 study by Geckman and colleagues. Mapping their findings, new knowledge on the x-axis, hallucination rate on the y-axis. Learning genuinely new facts happens much more slowly than aligning existing knowledge. As new facts are memorized, they linearly increase the overall tendency to hallucinate. While we are focusing heavily on mechanistic constraints here, you can find a full breakdown of the extensive data preparation burden this requires in the Medium article linked below. By contrast, research from Ovadia and colleagues in 2024 demonstrates that retrieval augmented generation, or RAG, consistently outperforms unsupervised fine-tuning on knowledge-intensive tasks. The data makes it clear. Attempting to teach models new facts via gradient updates makes the entire system vastly less reliable. This systemic degradation has a dramatic but medically accurate name: catastrophic forgetting. Because gradient updates are not surgical, a model fine-tuned heavily on specific domain data, like a large corpus of legal contracts, becomes better at legal language, and substantially worse at general reasoning and completely unrelated tasks. A common technical counterargument is the use of parameter-efficient fine-tuning methods, specifically LoRa. LoRa mitigates the risk by freezing the bulk of the pre-trained weights. It modifies only a tiny subset, protecting the vast majority of the model's general representations. However, empirical research explicitly shows that models using LoRa still exhibit significant forgetting when compared to an unmodified base model. Parameter-efficient methods manage the trade-off between specialization and general capability. They never eliminate it. So why do organizations spend millions of dollars only to discover these degradation issues during late-stage deployment? It stems from a sampling problem. A fine-tuned model will always perform better on in-distribution queries, prompts that look exactly like the fine-tuning data. If an engineering team evaluates the model strictly on these in-domain benchmarks, the measurable improvements create a false sense of security. The degradation occurs on out-of-distribution queries. That reflects how real users actually probe a system's limits, and it remains completely invisible during standard testing. A fine-tuning evaluation lacking a comprehensive out-of-distribution test set merely proves the model works in the narrow conditions explicitly designed to show it working. Avoiding these expensive mistakes requires precision. You have to diagnose exactly what kind of problem you are solving, which leads us to this architectural summary. On the left, if the model has inconsistent output formats, wrong tone, or poor instruction following, it knows how to generate text, but needs to generate it differently. Fine-tuning is the correct intervention. On the right, if the problem involves missing facts, outdated information, or proprietary content, those facts must remain external, verifiable, and updatable. RAG is the correct architecture. There are advanced synthesis paradigms like retrieval augmented fine-tuning, or RAFT. RAFT does not use fine-tuning to inject facts blindly. Instead, it fine-tunes the model's behavior, training it to strictly read retrieved documents, ignore external noise, and accurately extract citations. Before beginning any enterprise AI project, ask this diagnostic question. What share of the fine-tuning corpus is genuinely new knowledge, and would retrieval do it for less? You can read the full technical breakdown on Medium. Next time, in Episode 7, we will transition from architectural theory into the messy realities of responsible deployment. Training a model on your data undeniably makes it different. It only makes it better if the intervention matches the architectural reality of the problem.